Okay, last video on 4.1, Lord willing. Let's go ahead and get started. As promised, we're going to do a few transcendental functions. Y is equal to, let's do cosine x plus sine x, and let's look for on 0 to 2 pi. Okay? Now, let's go ahead and, we can obviously recognize, 0 and 2 pi are going to be very, very easy. Let's look for the critical values. So y prime is equal to negative sine x plus cosine x. And then we need to go ahead and set that equal to 0. Okay, which means I'm going to eventually wind up with tangent x is equal to 1, right? Push sine over to the other side and then divide both sides by cosine. I'm going to get tangent x is equal to 1. Where's tangent x equal to 1? Well, on 0 to 2 pi it happens twice, because remember the period of tangent is pi. Basically it happens at pi over 4, and then it happens, well, where? Well, it happens pi later, so it happens at 5 pi over 4. And so therefore it happens twice on that particular interval. And that tells me that, one of them, since this is probably an oscillating function, one of them is probably positive, one of them is probably a maximum, one is probably a minimum, okay? What I need to do is I need to go ahead and evaluate this function at the endpoints and at the critical values, right? Don't have to do a sign chart. It's on the closed interval. All I've got to do is evaluate and compare, which is beautiful. So y of 0 is cosine of 0 plus sine of 0. And just be very, very careful when you're doing this that you're actually evaluating the original function, right? Because you're looking for maximums and minimums of the original function. You don't care about the maximum minimums of the derivative, right? The derivative was merely a tool that you were using to analyze and evaluate a particular question that was asked of you about that original equation. So just be careful about that. Okay, 5 pi over 4, so cosine of 5 pi over 4 plus sine of 5 pi over 4, and then cosine of 2 pi plus sine of 2 pi. Well, it stands to reason that it probably returns back to where it was. So cosine of 0 is 1, sine of 0 is 0, so that's 1. This one's going to be the easy one as well. It's got exactly the same values as this one up here, so it winds up being 1 plus 0, or 1. Now, cosine of pi over 4, that's root 2 over 2. Sine of pi over 4 is root 2 over 2. Root 2 over 2 plus root 2 over 2 is 2 root 2 over 2, or just root 2. Now these have similar values, except for these were both positive, because that's in the first quadrant on your unit circle. These are both negative, because that's in the third quadrant on your unit circle. And therefore this winds up being negative root 2. Okay? Right here is your max, because root 2 is approximately 1.414. This is your minimum. Now, could you have foreseen this? Well, yes and no. You would have had to remember that sine x plus cosine x can actually be changed if you know to multiply by 1. Multiply by root 2, and then by 1 over root 2. And that gives me root 2 sine x cosine pi over 4 plus cosine x sine pi over 4. And as the sum formula, that winds up being root 2 sine x plus pi over 4. So if you remember that you can actually change that function into this, it winds up being a shift to the left of pi over 4 and then a stretch of root 2. which makes sense out of why these are the values where you get your maximum, and the maximum happens to be root 2, which is the stretch, and negative root 2 at 5 pi over 4. Okay? And actually to show you that, what I want to do, let's go ahead and get another equation out here. Let's do sine x plus cosine x. Okay, and let's sort of zoom out and look at this a little bit. And then I want to turn that off, and I want to do a new equation. And let's do square root of 2 times sine of x plus pi over 4. Okay, well, let's turn the other one on and see what happens. The answer is nothing happens because they're actually the same graph, okay? They're both on right now, and the reason why you can't see both is that one's on top of the other. So that's sort of a graphic demonstration that we've actually done our change of form correctly right here in terms of using our trig IDs. Now, I only do that just to sort of confirm and make sense out of what we got up here based upon, you know, our understanding of trig IDs and stuff like that. If you don't care, then fine, you don't care. But you are going to need those trig IDs, so I will continue to bring them up, if only just to remind you of them on occasion. Now, let's deal with this one on 0 to 2. Okay? Well, this is a product function between y is equal to x and y is equal to e to the negative x, which is, of course, one of the, basically the parent of exponential decay, or one of the parents of exponential decay. What we need, of course, is just to evaluate and find the derivative. So first, times the derivative of the second plus the derivative of the first times the second, and you can get e to the negative x 1 minus x. Okay, well that's kind of neat. I know that this is never going to be 0. It's exponential, right? There's no way to make that 0. It's always positive, because the only thing the negative exponent does, remember, is just flip things over. This, however, can be 0, and I know I get a critical value at x is equal to 1. Okay, so I basically just need to evaluate y of 0, y of 1, and y of 2. So y of 0 is going to be 0 e to the 0, or 0. This is going to be 1 e to the negative 1, or 1 over e. This is going to be 2 e to the negative 2, or 2 over e squared. Now, you may not remember what e squared is. It's about 7.4, but let's go ahead and remind ourselves kind of what these values are. So 1, and of course the e that doesn't require a exponential, like a little, that doesn't have a caret, is over here underneath the clear button. So second, that gives you, oh no, that's actually pi. It's actually the division symbol, sorry. So second, and then the division symbol, and we get 1 over e, and that's going to be equal to 0.368. And then we can get 2 over e squared, and that's going to be approximately 0.271. Now, obviously, minimum, maximum, right there, okay? From 0 to 2. Now, I don't think it would be a bad idea to go ahead and actually look at that graph. I never think it's a bad idea to look at the graph. And I think that's an important part that sometimes gets sort of lost in the mix. So we know that it's going to be e raised to the negative x, okay? And let's go ahead and sort of drag that out. Let's zoom in, and I know that I'm going from 0 to 2. So we see the fact that it's just barely, I mean, it doesn't even get up to 0.4 right here, which is why we can sort of make sense out of the 0.368 value at x is equal to 1. So it starts here at 0, 0. We got that value. We got 1.368, and then we got 2.271. And that right there is just a little bit lower, but we can tell that on the interval from 0 to 2, because those are the only values I'm worried about, the minimum on that closed interval is over here at the origin, and the maximum is here at 1 over e. Okay? Now, let's go ahead and move on to another one, which is sort of related because it has to do with natural log. Let's deal with y is equal to x minus natural log x, and I want to deal with it on the interval 1/2 to 5/2. Okay. Now, let's go ahead. Now we know that the limiting factor, not factor in terms of multiplication, but the limiting thing, the limiting term in terms of domain is going to be this natural log, right? So we know that the implied domain is 0 to infinity, non-inclusive of 0, okay? But we've been limited even further than that. And this actually is within that domain, so we know that this is possible. And we can go ahead and take the derivative, and that's going to be 1 minus 1 over x, which of course is going to be x minus 1 over x. Now I happen to know that my critical values for this, if I just take this into account, are going to be 0 and 1. Okay, well the critical values at x is equal to 0 and x is equal to 1, the critical value at x is equal to 0 fails for two reasons. First of all, it isn't even in the implied domain of the original, right? And second of all, it's not even in the closed interval that we're entertaining. The only critical value that we're worried about here is x is equal to 1, okay? And therefore, let's go ahead and say, well, y of 1/2, y of 1, I keep wanting to do something other than what my mouth is saying. And this winds up being 1/2 minus natural log 1/2. This is 1 minus natural log 1, and this is 5/2 minus natural log 5/2. And of course we can use our calculator to evaluate all of those. That shouldn't be too tough. Okay, let's go ahead and go 0.5 minus natural log 0.5, the only time that you'll ever see me using decimals, or one of the only times. That's 1.193. We get 1 minus natural log 1, and that's going to be 1. We actually get an actual value for that. 2.5 minus natural log 2.5, and that's going to be approximately 1.584. Okay? So we obviously have our maximum here and our minimum here. And we should know kind of what this original function looks like. I mean, it's a difference function based upon two functions that we actually know, right? Let's go ahead and plug it in here. Let's do x minus natural log x, and then we can do y1 minus y2, and let's go ahead and change the window. Let's go 0 to 10, and then maybe -5 to 5 originally, okay? There's y is equal to x. There is y is equal to natural log x. And then, of course, the difference function is going to be coming along here, I think in black. And there it is, okay? Now, let's go ahead and zoom in to the interval that we've actually been given, okay? So if we go 0.5 to 2.5, and we know that we can go ahead and get rid of those and just go 0 to 3 on the y, there's y is equal to x on 1/2 to 2.5. Here comes y is equal to natural log x, not that it really matters, and here comes the difference function, and we see that minimum right there at x is equal to 1, okay? And then, of course, it goes up from there on both sides. It just happens to go up just a little bit farther at 5/2, or 2.5, to give me my 1.584. Okay. Now, let's go ahead and do one more example really quickly before we sort of adjourn for this little for this section in the book. So we have y is equal to 5 arctan x minus x, and we're going to limit it from 1 to 5, okay? Now, we ought to probably be able to figure out kind of what that looks like, because I should know what a vertical stretch on arctan looks like. Arctan, of course, is between -pi over 2 and pi over 2 on the y, and then you stretch it by 5, and then you subtract y is equal to x. I'll show you the graph here in just a second, but let's go ahead and get that going. So we have 5 times 1 over x squared plus 1 minus 1. Okay, well, that winds up being 5 over x squared plus 1 minus x squared plus 1 over x squared plus 1. And the reason why I'm doing that is it winds up giving me 4 minus x squared over x squared plus 1, which of course is 2 minus x, and 2 plus x over x squared plus 1. Now that denominator is certainly never going to be anything, so we don't have to really worry about that. But x is equal to 2 is in here. I do have two critical values, right? X is equal to negative 2 and x is equal to 2. Well, x is equal to negative 2 is not in the closed interval that we're entertaining. But I do know that I can evaluate at 2. So let's do y of 1, y of 2, and y of 5. So we have 5, and I'm going to use the inverse tangent right here simply to save space. Inverse tangent of 2 minus 2, and 5 times the inverse tangent of 5 minus 5. Well, inverse tangent of 1 ought to be easy enough. Inverse tangent of 1 is pi over 4, so 5 pi over 4 minus 1. But we can go ahead and plug those in. So how about 5 inverse tangent of x minus x? And if I do that, then basically all I have to do is y1 of 1, y1 of 2, and y1 of 5 in order to evaluate all three of those. And I see the fact that y1 of 1 is kind of in the middle, so it's going to be neither my maximum nor my minimum. 3.536 and 1.867. Y is equal to 2, x is equal to 2, so 2, 3.536, that's my maximum on that particular interval, and 5, 1.867 is going to be my minimum, okay? Like I said, we can go ahead and let's go and delete, and we have negative x, and then we'll just add y1 plus y2 on the interval from, let's go 1 to 5, and let's go 0 to 5. That blue line up there was the 5 inverse tangent. You can't see though, actually, yeah, let's go ahead and stop. Let's go ahead and zoom 6. Here is 5 arctan of x, and we should remember this shape. It's just the arctan of x function. There's the negative x, and then when I add those together, it should make sense out of this black function right here. Okay. Of course, what do we notice about the black function? Okay. And of course, we see the fact that there's a maximum right here, and of course that maximum winds up being here at x is equal to 2. We're coming up on about 19 minutes. I think that's enough, especially since we're kind of beyond the calculus and we're going back, and I'm trying to pull forward some of our previous knowledge on combination functions and how those graphs help us understand it. You would be surprised at how many things on the AP exam, if you just remember all the stuff that we went over in Algebra 2 and Pre-Cal, you don't actually need calculus, or at least it's a wonderful supplement to the calculus that you're being asked to do. I will get on, hopefully relatively soon, some videos for 4.2. 4.2 is extremely, extremely important, but we will talk about that then. Bye.